Hello, everyone. Hello, everybody. Welcome. Thank you for joining us today. My name is Nicholas Karam. I'm the new regional sales engineer with Bekaert in the building products group. I'm a structural engineer. I have my PE license in New York and California. Previously, I worked in the suspended access industry. For the past 9 years, I worked on large high-rise building projects, helping them, access the sides of their buildings for window washing. In my new role, I'll be working very closely with Claire, focusing on our Dramix Steel Fibers. And I really look forward to getting to know all of you and to working with you in the future and to help you in any way I can on your projects. I put some notes in the chat there, but for today's webinar, we recommend you use Google Chrome. It just tends to work the best out of any browser. So if you have any issues, please try to use Chrome first, and then, if the problems persist, just let us know, and then we can troubleshoot for you. Any questions throughout the session, please use the chat feature, which you will see that I have already put in quite a few chats in there already. So you can use that same chat feature to ask any questions throughout the session. And then at the end, we will go over all the questions. And if we run out of time and we can't get to your questions, don't worry, because either myself or Claire will reach out to you afterwards and answer all the questions that you have. Lastly, for any PDH credits that you may need, please email me. We will get you your certificate. I put my email in the chat there. It's nicholas.karam@bekaert.com. Again, thank you for joining. And so with that, I'm going to pass it on to Claire, who's going to tell you all about our SigmaSlab. Thank you.
All right. Thank you, Nick. Welcome, everyone. Thank you again for joining. I know some of you, but not all. So quick introduction. I am Claire Gandy. I'm the sales engineering manager for the U.S. division with Bekaert in the building products group, specifically focusing on Dramix Steel Fibers. So for the next 45 minutes or so, I'll be talking about this new, my screen went away. We'll be talking about this new SigmaSlab solution, the innovative and sustainable flooring solution. And we're really excited to share this with you. This is something that we feel really excited about, and I'm really interested in hearing your feedback and opportunities to share this with you here in the States. So with that, I will jump in. So first of all, what is SigmaSlab? Well, it is a patent pending solution, and we will be going through it, starting with the name. Now, why SigmaSlab? Where did this come from? Well, if you think of the Greek letter capital Sigma, if you see that in a mathematics setup, you would think of that as a sum, and that's exactly why we chose it. It is the sum of two complementary reinforcing systems. So in this case, it would be the high performance Dramix steel fiber reinforcement and the high performing CCL post tensioning systems. In addition to the sum of these reinforcement approaches, it's also the sum of these two multinational companies, Bekaert and CCL. And I do want to be clear and upfront that while there are other steel fibers out on the market and other post-tensioning systems in the commercial space, this patented system is specifically with Dramix Steel Fibers and CCL post-tensioning. Now, it really does come down to stresses. And so again, this name of Sigma ties back to, because the lowercase sigma, for those of you structural engineers on the line, we're used to seeing lowercase sigma refer to stresses. And that's exactly relevant here. So Dramix Steel Fibers work on basically as a passive reinforcement, meaning that they start to work after the concrete cracks. And as a result of this, once they start to work, they provide a post-crack residual flexural strength and thus give ductility to the concrete system. The design process that we use is an inelastic approach, specifically this yield line analytical method. Post-tensioning, on the other hand, works on an active reinforcement principle. What that means is by pre-compressing the section, you are in a way indirectly increasing that first crack strength, and thus it becomes an active reinforcement. So once it cracks, if you have a PT only solution, there is no post-crack capacity, and then the failure mode would be brittle with no ductility. The design approach for a PT only system would be an elastic method. So let's dive a little bit deeper into each of these reinforcement approaches. So with Dramix, some of you, especially here in the States, may not be familiar with steel fiber reinforcement and how it's used for flexural purposes. We are a European company, Bekaert. We are based in Belgium, and thus we use a European standardized test called EN 14651 to characterize the post-crack flexural performance of a steel fiber reinforced concrete matrix. When we get those results, we are able to then simplify them in a way to a constitutive model in such that we can transform those flexural stresses into tensile stresses. The end result being that we can calculate the section moment capacity. Now, if we look at the post-tensioning, this is a system that's far more common here in the States. Probably many of you may already be familiar, but if you're not, I'll give a quick overview as well. That the CCL post-tensioning, at a high level, it provides pre-compression to the system. And the way that this is done is you have post-tensioning tendons. These are high-strength steel cables that are insides of ducts or sheathing, and they're positioned in specific locations before the concrete is placed. Then once the concrete has gained sufficient strength, then the tendons are pulled or tensioned and anchored against the outer edges of the concrete. And that provides a squeezing or a pre-compression of that section. And so if you look at this image in the top left of the screen, where once a section goes into bending, the bottom portion, in a typical, positive bending scenario, the bottom is going into tension. And so by pre-compressing that section first, you are providing an additional stress over which that load has to go through to get to that tensile member. So you're actually increasing the initial cracking load like we talked about earlier. So it really is the best of two worlds. We're taking one system that is strong in bending, right? Dramix steel fibers are very strong and effective in flexure, but they are weak when it comes to direct tension. And by contrast, post-tensioning, or I'll often refer to this as PT throughout the duration of our time together here, PT is very strong and effective in direct tension, but more weak in bending stresses and certainly in cracked concrete. So the way that this would work in combination in practice would be that the Dramix steel fibers would be used for the loading, the flexural stresses from loading, and the PT tendons from CCL would be used for the tensile stresses from the concrete shrinkage. So there are 3 SigmaSlab systems that are available: SigmaSlab G, P, and E. G stands for ground supported slab. So your slab on grade. So for unrestrained seamless floors, jointless floors up to a spacing of 230 feet, as well as heavily loaded racking, foundation mats, or exterior heavy duty pavements. SigmaSlab P, the P stands for a pile supported ground slab. Now I use the term pile kind of generically. This can apply to, helical piles, rammed aggregate piers, CMCs, and so on. Really any kind of discrete soil improvement element where the slab is spanning from element to element rather than getting a uniform K value. Additionally, we can look at seamless floors. Seamless floors meaning this is a floor where there's no visible joint. Also SigmaSlab P would be applicable for longer pile spacing and floors with heavier load. So this gives us more range with a reinforcement solution for those kinds of more challenging design conditions. And then SigmaSlab E, the E standing for elevated. So this would be for a full or partial replacement of rebar in an elevated cast in place application. So this could be for floors with large spans, heavy loads. Think of this for residential or hospitality, generally commercial type structures. Now, as far as scope of our conversation here today, we will be focusing on SigmaSlabs G and P, the on-grade levels. I will give you just a little bit of more information on SigmaSlab E, but that really is not the focus or highlight of this session here today. There will be more on that to come in the future. So let's take a deeper dive into SigmaSlabs G and P. So first, thinking about seamless floors. When I say seamless floor, what I mean by that is no visible joints. So currently, the Dramix solution for that would include Dramix plus some continuous top reinforcement, which could be a welded wire mesh or rebar, in which case we can handle a fully restrained system. By contrast, the SigmaSlab solution would really be applicable for an unrestrained solution. But with that, we can have joints up to 500 feet, very slim slab sections. The dosage of steel fibers would be about the same, but you can see the weight of steel would be significantly reduced from, again, that top mesh, whether it's rebar or welded wire, or going to post-tensioning. And also the GWT, which stands for global warming potential, which is essentially that carbon footprint in a way of speaking. You can see a pretty significant reduction there as well. So our total cost reduction from 10 to 25% in savings and 10 to 20% carbon footprint reduction. Well, let's move now into jointless floors, spans up to about 230 feet. Currently here in the US, our jointless floors that are fiber only range around 130 feet. That tends to be the upper limit. Whereas with a SigmaSlab solution, we could go up to about 230 feet, almost double what we're doing in practice today. Again, very slim sections possible, dosage about the same. Now we are adding steel, but we are reducing the joints pretty significantly and also reducing that carbon footprint. So we're seeing about a 5 to 15% reduction in both cost and carbon footprint. Now let's switch over to the pile supported slab comparisons. So floors on and again, I'm using pile, term loosely, but now we can have, again, slimmer sections, 230 feet roughly joint spacing, lower Dramix dosages. And now one of the real benefits of using post-tensioning in a pile supported system is the ability to contour or vertically profile the tendons to really help. It's very similar to the way that you use post-tensioning in elevated applications. So you can really optimize the benefits of the post-tensioning in this type of application. So on this case, we see about a 5 to 15% cost improvement and about a 10 to 20% carbon footprint improvement. Looking at seamless floors on piles, again, no visible joints now. Here, again, restraint is one of the main things that we'll want to keep an eye on, but we see really significant joint spacings possible and on average, about 10 to 20% savings in cost, as well as a much faster construction and 15 to 25% improvement on your carbon footprint. We're going to continue through looking at the SigmaSlab P for now larger pile spacing. So there is a limitation now where if you have a fiber only solution, or if you have a fiber plus rebar solution for a pile supported floor, there are some limitations to how far the pile spacing can go. And now with post tensioning, we have more opportunity to provide a cost-effective solution. So here we see joints. You know, now we could have been before around 20 feet with rebar plus Dramix, whereas with the SigmaSlab, we can go up to about a 30-foot pile spacing. And we see on average about 5 to 15% cost savings. And again, a pretty significant improvement in construction speed, as well as a really notable reduction in carbon footprint, 20 to 30%. And very similar now if we look at a pile supported floor system with very heavy loads, right? On average with a rebar plus fiber solution, we can be at about 1250 PSF uniform loading, whereas with SigmaSlabs, we're looking at about a third increase over that, so 2100 PSF. And so now not only do we have a heavier load condition where we really didn't have maybe a great solution before, now we are also still offering that carbon footprint improvement up to about a 15% reduction. So to try to, I'm a visual person myself, so I find this table very useful. Say, okay, you know, when it comes to the relationship between your pile spacing and your uniform loading, you know, when might one solution or another be appropriate? Now, when it comes to post-tensioning, here in the US, the most typical approach is to use unbonded strands. They are cheaper than bonded. They are easier to apply and install. And usually what we find is if the contractor is new to post-tensioning, we can train them. When I say we, I'm thinking more about the CCL side. They can be trained and then continue installing that from there. Bonded PT is a slightly different system where there's actually a duct that the PT is run through, and it is grouted with a grout system after it's tensioned so that you have a fully bonded system in a slightly different way than the unbonded PT. It is, as a result, a little bit more expensive than the unbonded system to construct, and there is special grouting equipment needed. But again, after the initial training, the flooring contractor could then continue installing those systems. So where we see these two types of solutions being used, you know, bonded PT is not as common here in the US. It's used pretty widely elsewhere, but we definitely see a reason for having both solutions available. Unbonded PT is certainly appropriate for all types of warehouses and pavements, but there are some exceptions where you might want to use a bonded solution. Meaning maybe you have a facility where the owner will be making a lot of cuts or cores moving forward, where they're going to have to make some layout changes in the flooring solution. And certainly in that case, a bonded solution would be appropriate. Or where if you have a warehouse with racking and the post-installed anchors are deeper than the cover to the post-tensioning cables. Or where, you know, it's a road system where certain portions might be removed. Let's say you have underground utilities or something like this where we know that that is possible. So that might be another reason to use a bonded PT system. Now, sorry about this slide. I know there's a lot going on here. The way that this webinar platform works, I can't have animations. So unfortunately, everything is showing up all at once. So hopefully I'll walk you through it my best I can, and hopefully it'll make sense. But let's look at these different systems and how they work, their behavior, to try to get an understanding of why SigmaSlab is being proposed. So in the top left, we have an unreinforced slab. So what we're looking at is a slab in section. And we're going to be looking at these red and blue, and in the bottom curves green. Those curved lines are the moments. So starting with the red line in the top left image, let's say this is 1 pound less than the cracking load being applied to an unreinforced plain concrete slab. So when you apply that load, you'll get some moment curve that looks something like this. Positive moment demand in the bottom, right where that load is being applied, and some negative moment adjacent to it. Now, let's say we add 2 more pounds to that, sufficient to get past that cracking threshold, and that section cracks. So that's the blue lines here showing the crack right underneath that load. And then we basically shift and completely change the moment curve, because now at that point of the crack, there's no bending moment capacity. That capacity goes to 0, and then we shift the moment into negative space. So let's then move to the right, where we have a Dramix steel fiber only solution. So in this case, we start with that same red load where the behavior is identical to what we just saw before. Because again, this Dramix steel fibers are a passive reinforcement. They don't start to work until the concrete cracks. So then now we have the smaller blue loading arrow coming in. Again, let's say that's 2 pounds more to get us past that cracking threshold, where we have cracking right underneath that load location. Now we have a slight loss. This is that the second curve that's just kind of mirror image to the red one and just above it. So we still have positive moment capacity because of the post-crack flexural strength from the steel fiber reinforcement. Okay, well then let's exploit that and add an additional load. That's the lighter blue arrow and curve that comes with it subsequently. And so what that does is it actually flattens out the point of the positive moment capacity and moves the moment. We have a stress redistribution capacity with the steel fibers that pushes that moment curve upward into negative moment, creating a yield line or a plastic hinge adjacent to some distance away from that load application. And so this is really the crux of why we use the yield line methodology in our analysis. All right, well, let's switch gears a little bit and instead move to the bottom left image, which is PT only. So now that same red arrow is true. We apply that load and that moment curve is the same, but now we then tension the steel cables. And so now we are applying an additional load where we have an additional load capacity, right? We have that additional pre-compression. So you have a higher load capacity. Then when we get to a point that additional load is applied such that that cracking threshold is crossed, we have a crack in the slab. And now we have that same post-crack, looks like my image isn't, my video isn't working. It looks like the post-crack behavior then is being taken over by the Dramix steel fibers. So you see that that's where the post-crack ductility of the steel fiber solution would come in handy. And that's the image that we see over here on the bottom right. So now we're combining these two systems. So again, pre-crack, the moment is the same. You add post-tensioning, we have an increased load capacity. We add then additional loads to crack the section and then to cause the negative moment yield line. And so we have an overall total load increase capacity and a very ductile system. Hopefully that makes sense. Now, similarly, we can see the same thing for a slab on piles, the SigmaSlab P, where with a pile supported solution, if you had a conventional or plain concrete system, right, where you have your initial loading prior to cracking, the behavior is as you would expect, some negative moment over that pile support, some positive moment adjacent to it. And when you add additional loads in blue to get past that cracking threshold, you would anticipate the negative moment being reached from a cracking standpoint, and we would then have two independent acting slab sections on either side of that support. Moving to the right-hand side, I promise this slide is so much better with the animations. I'm sorry. So on the right-hand side, you can see the slab now with a Dramix fiber-only solution. So behavior is the same for pre-cracking loads. Once additional load is applied to that system where it cracks, we now get that ductility, that post-crack flexural behavior that we're counting on from the steel fibers to distribute the stresses out into the adjacent portions of the system. Going to the bottom left, very similar to what we saw before, except for now everything is flipped, right? So now we have that additional negative moment capacity over the support because of the post-tensioning and the pre-compression. And then as we add additional loads, we then have the ductility. We don't have the ductility from a PT only solution because there's no fibers yet. So once you get to a point where that solution cracks, you basically end up with the same thing that you would as if it was unreinforced. And then it brings us over to the bottom right, where when we combine these two solutions together, we get that increased crack capacity and then that ductility post-crack from those two solutions. So in summary, the stresses from the forces on the slab are taken by the Dramix steel fibers, right? So there's also the help from the section's pre-compression from the PT, not to mention the fact that the PT is allowing for the larger joint spacing. So where you have higher loads, you would expect to see a higher dosage of the Dramix steel fibers. Where you have higher joint spacing or a higher degree of restraint and friction, then you might have more closely spaced PT tendons. The stresses from restraint shrinkage in the concrete would be taken by the CCL post-tensioning. When you need a smaller crack opening, that would likely result in a higher Dramix dosage as well. And overall, again, that cost and time-saving solution. So let's look at a case study. This is a project for Tesla in Berlin. As it turned out, we were already working on the project and providing a traditional Dramix complementary solution, which is the Dramix steel fibers plus continuous rebar or mesh. And at the time that we were working on this, SigmaSlab was still kind of in development. So this is a case study looking at what would have happened if we were able to have gotten SigmaSlab done in time. And in fact, we weren't able to, but we have a very nice parallel train here to study the two solutions side by side. So looking at joint-free options for Tesla in this project in Germany, it had a 400 foot by 400 foot max floor area, 5,000 PSI concrete, and there were robots on the floor. That was actually the controlling design criteria. So the combi slab solution was a 9-inch thick slab section with a 6'6" W8 by W8 top and bottom. So pretty heavy welded wire mesh plus 42 pounds per cubic yard of the Dramix 40-65-60 BG steel fibers. Now, any of you who might not be familiar with what the different steel fibers mean, please just reach out to me and Nick. We can get you an intro and overview to the steel fibers. We're not going to go into that here today. So by contrast, when we looked at the SigmaSlab option, in this case, we were able to thin it by 1 1/4 inches down to 7 3/4 inch thickness with 5/8 inch diameter tendons at 4 feet on center in both directions with 50 pounds per cubic yard of the same Dramix steel fibers. So how do these compare? Well, first, let's look at sustainability. I know here in the States, sustainability is starting to get more traction. Certainly our European colleagues are dealing with this a lot more. It seems like there's a bigger push for this in current moment, but certainly I'm personally hearing more about this from several owners that I'm working with. So I definitely believe that sustainability is going to continue to become more and more of a driving part of the conversation on our projects. So there are global sustainability goals, as all of us, I'm sure, have heard, right? There's the Kyoto Protocol, there's the Paris Agreement, the ultimate goals of which are to reduce greenhouse gas emissions worldwide. Now, there are a number of contributors to greenhouse gases, right? It's not just carbon dioxide, although that is the one that we hear about the most, but there's also methane, nitrogen dioxide, and hydrofluorocarbons. So there is some amount of warming that is natural, just based on the Earth's atmosphere and so on. There's cyclical nature to warming and so on. However, there are human effects, and what science has shown is that the human contribution to greenhouse gases has increased disproportionately over the last 100 years or so. So it really is important that we make efforts worldwide to control this, because of course it has very significant and lasting impacts. So we're moving in this direction, and how do we get there? So see if I can get there we go. One of the most measurable parameters is the CO2 equivalent. So a CO2 equivalent is defined by this equation, which is then in turn linked to this GWP, which stands for global warming potential. If you look at this map on the right, globally, there are a number of us who are the worst when it comes to carbon equivalent emissions per capita. Obviously, the US and a number of other nations have a good bit of work that we can do to recover some of the impacts of our activities. Now, there's also a concept of something called an environmental product declaration, or an EPD. So this is something that people will create. And in fact, Bekaert has one for our Dramix Steel Fibers for a number of our manufacturing facilities to understand what is the actual impact of the actions that we're doing to create these products. So this is a third-party, verified, independent solution to understand, what is the environmental performance of a specific product, and it's looking at it from cradle to grave. And ours is shown here, but really what we're trying to understand is that total global warming potential as it's expressed in pounds or kgs of carbon dioxide equivalent. So when we look at all of the different data going into manufacturing Dramix Steel Fibers, we see that 1 pound of Dramix has an equivalent of 0.88 pounds of carbon dioxide. And this is dependent on, again, that total cradle to grave evaluation, looking at the extraction of the raw materials, processing the materials, transporting it to production site, and then the actual manufacturing process. So you can see here a comparison from that GWP, or that pounds of CO2 equivalent, for typical steel, PT steel, steel fibers, and concrete. So coming back to the solution in this case study in Berlin, we have there were three. The initial one that I've kind of skipped over up till this point was the original rebar approach. So that had a contribution of about 322 pounds of GWP or CO2. The complementary solution, that 9-inch slab with the double mat of mesh, a little bit less. And then we see the SigmaSlab option down in the 230s. So there's a pretty significant reduction as we go from one option to the next. Now, it is kind of hard to visualize what does all of this mean. Numbers are all well and good, but putting it in a slightly different way, a 25% reduction in CO2, equivalent CO2, compared to the as-built condition, which is the Dramix Combi Slab, that's a 2,400 ton difference of equivalent CO2 savings that we could have offered with the SigmaSlab option, which is the equivalent of about 15,000 trees, mature trees, or a mature forest over 1 million square feet in size. Right, so if you just tell me, 2,400 tons, like I don't really know exactly what that means, but if you tell me 1 million square feet of forest, like I can picture and really visualize the impact of what it would mean to eliminate a forest of that size or to plant and create one consequently. So I find that very useful personally. All right, well, all of that is well and good, but how does it fare when we compare cost? So as we showed earlier, right, we have the as-built, which is the 9-inch thick with the 6.6 W8 top and bottom with 42 pounds of steel fibers compared to 7 3/4 inches thick with a 5/8 diameter tendons at 4 feet on center. So there is a cost savings, as you can see here. We dive into that a little bit more in the next slide, where we look at, again, that conventional solution versus the traditional combi slab. The one in the middle in the yellow at the bottom is what was built, and then the green in the right-hand column of the table is that SigmaSlab option. And it was about a 20% cost savings from the conventional solution compared to SigmaSlab, which in this particular example would have been a $700,000 savings. Not to mention the time and the long-term maintenance improvement, as well as there's something that's coming up that I've heard from my colleagues in Europe. I don't know when or if this will happen in the US, but there's a potential that owners or developers or contractors will have to pay a fee or a penalty based on the amount of carbon emissions from their specific project. So if that would take place, they're looking at a cost of $70 per ton of CO2 emissions. And so that would have then resulted in an additional $175,000 in savings if they were able to circumvent that fee. All right, so all of this sounds nice, but what about in real life? How has it worked? So if you think about who the people are in the conversations that we're having about these floors, right? Let's think about the real estate investors, the owners, the asset users, so to speak, right? So you can use your asset very flexibly. It gives you an amazing opportunity to repurpose or reutilize that space as your needs change. Again, that lower carbon footprint, about 15% less steel being utilized. We have that improved floor durability, so you have lower maintenance costs in the facility. That larger joint spacing, again, up to about 500 feet. That means that all of the tires, the equipment going over those joints will then also have an improvement in their lifespan and a total cost of ownership savings of about 10% compared to a traditional combi slab with Dramix. For the contractors, the flooring and the PT contractors, you can anticipate a lower labor cost, less man hours or woman hours needed on site, faster project execution, and less risk of delays. This is huge, especially in the current market where people are building so fast and furious, so to speak. Really getting into the facility faster makes everybody happy. There's improved safety. Of course, we want to make sure everybody working on the project is as safe as possible. And this is a less commoditized business. So this is something that you can use to differentiate yourself as a contractor in the market, that you're not just doing the same thing that everybody else is. You have really a new value added proposition when it comes to high performance flooring. So here's an example of an outdoor pavement for Aertsen. This is a project that was an outdoor pavement adjacent to this warehouse for a new loading bay area. So this was a really great example of optimally combining the Dramix Steel Fibers with the CCL post-tensioning for this fast, safe, easy installation process. And the contractor on this project was Del Porta. They were very happy. The owner of the project was really thrilled with the long lifespan and lower maintenance cost expectations. Here's another project, couple project in Mexico. This was another slab on grade, so SigmaSlab G application, about 600,000 square feet. The slab thickness was 6 3/4 inches with 42 pounds per cubic yard of the Dramix 4D 6560 fibers. This project, they did actually choose to use bonded PT, which were spaced two strands per duct. Every ducts were at 11 3/4 feet on center each way, with joint spacing 330 feet, where the flooring contractor on this project was RCR. So we have two really exciting examples of SigmaSlab. And in fact, this couple project, I have a little video. Now, this is a project that we have a longer video. I'm not going to make you watch the whole thing here, but we have a short video that I'll just show you now to give you a sense. I think it's really nice to see it in action, and I'll let the video do the talking from here.
Bekaert is a leading global company in the transformation of steel. Innovation is a fundamental part of our DNA. SigmaSlab is the technology that combines the technical, practical, and economical advantages of Dramix Steel Fibers and CCL's post-tensioning system benefits. The Coppel Logistics Center is the first SigmaSlab built in the Americas and the second in the world. For this project, 4D steel fibers were used, which resist the forces acting on the floor as well as the stresses from post-tensioning. For this floor, 100 by 100 meters panels were built. However, the combination of both technologies allows for panels up to 150 by 150 meters. In addition, SigmaSlab reduces the carbon footprint of concrete floors by up to 25%. Due to new logistics, distribution, and storage challenges, customers demand more durable and sustainable floors. SigmaSlab is the answer.
Okay, so I love that. I love to see those project videos. We do have, as I mentioned, a longer video. Nick is going to put a link to that in the chat. So if you would like to get a better sense of what went into the construction process on that project, please go ahead and check it out. So really, what is the bottom line here? From an advantage standpoint, right? Cost savings, better direct savings to various, members of the project team, including the owner. You have very high quality, crack-free, low maintenance floors, so lowest total cost of ownership. Your social responsibilities, we have a very low carbon footprint, and your people, it's easy to install. There's less trip and fall hazard, so it is very ergonomic for your labor force. Your advantages, right? We're all having to work as quickly as possible. I don't know about you guys, but I'm as busy as I've ever been. So this is something that we can execute really quickly from both a deliverable standpoint on the design as well as on the actual execution of your floor system. And it really is combining the best of two worlds with the Dramix Steel Fibers and CCL PT. And our commitment to you is we understand that this is a new type of solution for many of you. So you are going to receive the highest quality service and attention from both Bekaert and CCL, as well as job site support and potential training if needed from CCL. All right, and just in the last couple of moments here, I know some of you on the line are probably interested in the elevated applications for SigmaSlab E. So just a little bit on that as we wrap up. So what is SigmaSlab E, right? This is a cast-in-place concrete slab using CCL post-tensioning as the primary reinforcement. So this is a departure from what we do on grade, where Dramix is usually the primary force-resisting solution. Now in a SigmaSlab E, the PT is the primary reinforcement. And now you use Bekaert Dramix Steel Fibers as a substitute for rebar and for punching reinforcement. And it can be built with or without additional rebar, depending on the requirements of the particular project. It meets or exceeds all of the performance requirements and expectations of a traditional PT and rebar slab with regards to fire, durability, insulation, thermal, and so on. And there are significant benefits with regards to using less materials, less labor. It's faster, the sustainability impacts, the cost efficiency, and it is tested and proven. So this is all based on testing that has been done at Virginia Tech. I say there's 4+1 test slabs. This research was co-sponsored by Bekaert, CCL, and PTI, the Post-Tensioning Institute. There were originally 4 test slabs in the scope of this testing, T1 through T4, which are listed here. Banded uniform is T1, so that's the control slab, similar to what's going on every day here in the States. T2 is banded uniform layout, replacing all of the rebar with Dramix 5D steel fibers. T3 is a banded configuration of post-tensioning with rebar. T4 is a banded with a complete elimination of rebar using Dramix 5D fibers only. And the results of that 4 slab testing scope were so positive that a 5th test slab was added, T5, which is a banded bonded solution. So T1 through T4 are using unbonded PT, and then the T5 was bonded PT plus Dramix 5D steel fibers. So the results of T4 and T5 were overwhelmingly positive. They both resisted more loads than any of the other test slabs. Now, as many of you will know, changes to ACI code, PTI recommendations, these are all going to take some time to be implemented. However, we do have a new IATMO report in process specifically for SigmaSlab E applications, and that is about to be published imminently. So really, I'm waiting on that any day now, so to speak. So this is something that we can start putting into practice here in the US very soon, although we have already been doing this globally in a number of project examples. Obviously, the 2 images here, not necessarily the same project, top and bottom, but just to give you a sense, right? If you've ever been on a elevated PT job site, you know how congested those can get. And the bottom image really is, that's a real SigmaSlab application. It can be just that simple. And you see from a safety standpoint, from an ease of execution standpoint, it is pretty clear what the opportunities would be for using this in projects here in the States. And with that, I will say thank you so much for joining. I'm really glad that you took some time out of your very busy schedules to join us to talk about this. And with that, I'll pass it back to Nick if there are any questions that I can answer for you.
Thank you, Claire. Okay, let's look at the questions here. We have one from Terry. Terry would like to know, are the PT strands placed in both directions, allowing for a max of 230 feet placement of the slab in both directions? So 230 by 230 feet, is that possible?
It is possible. So it really depends on the configuration of the project. So if you remember the first slab example, that pavement that we showed that was more rectangular, that only had PT in one direction. So if you have a kind of long and thin strip, then you might only have PT in one direction. Or if the floor surface allows, and you can have, in fact, we can go up even further than 230 feet. That's just for the jointless type approach. So yes, absolutely. In that case, you would have PT in both directions, and you could have a square area, like you said, 230 by 230.
Great. Rex has a question. What are the tolerances for strand positioning?
That is a good question that I don't actually know the answer to off the top of my head. I would have to look into that, but I think that there are specifics to that our friends at CCL would be able to help provide some guidance on if there was any question on how to specify it or what to look for in the field. So we'll double back on that with you, Rex, and follow up with you later.
Okay, back to Terry. Does the PT forces do the PT forces increase the potential for curling in thin slabs?
No, they should not. The way that these slabs are analyzed, all of those various forces are taken into account, as well as the location of the post tensioning within the slab section. So there should not be any additional risk of curling, especially because these slabs are going to be anchored usually to adjacent slab panels with proper jointing. So I would not anticipate that being a concern.
Okay, so the next question by David kind of plays off that. Are the strands continuous through the joints?
Right. So usually the joint spacing has to do with how long a PT cable can actually be. So oftentimes, depending on the configuration of the floor, you would have a kind of pour strip. So basically where two adjacent panels might come to one another, there might be a few feet wide strip that would just have probably rebar going through it to basically bridge those two slab panels together. The PT may also, there are other options. There's intermediate slab anchors. So depending on the way that floor is laid out, if it makes sense to use an intermediate anchor to continue the tendon through the joint, then that might also be a possibility. So this is something we're bringing in our partners at CCL to review the actual floor system specifically, and not talking in generics, but really looking at your project to say, oh, because of X, Y, or Z factors, we can approach it one way versus the other.
Great. Yeah, that was David with that question. I forgot to mention that. Thank you, David. We will move on to Miguel. Are the numbers on GWP calculated using conventional concrete or mineralized CO2/reduced concrete?
Miguel, I would have to double check on that, on those specifics. My suspicion is that those are done with typical concrete, but I can look into that. Nick and I can do a little bit more research to find out for sure, and we can let you know.
All right, back to David. Does SigmaSlab allow one to increase saw cut spacing in slabs?
Great question. So David, there wouldn't be any saw cuts. By using SigmaSlab, we would eliminate saw cuts. So the joint spacing that I'm talking about, those are basically day joints or construction joints. So these might be dictated by, as I mentioned a few moments ago, the length of the PT cables, but it could also be dictated by the amount of concrete and cement that you can get on any given day from a specific concrete ready mix supplier. So wherever those joints would be, then you would move forward, but we would not be saw cutting these floors.
Okay, back to Terry. Is the SigmaSlab adaptable for super flat floors?
Yes, it is. So usually a super flat floor is going to be constructed as a very narrow aisle, in my experience. So long, thin strips where you can execute it and really control it using a laser screed. And absolutely, this is an application where I would anticipate the PT going only in the long direction, and then you're controlling stresses in the short direction with the Dramix Steel Fibers alone. So that's actually a really excellent application for SigmaSlab.
Okay, so we might have touched on this before. How are the post-tensioning strands tied off at each end? If the final slab is 1,200 meters by 1,200 meters, are the strands continuous throughout? I think you might have touched on this. But...
Yeah, so more than likely, you cannot get a single tendon strand that is actually 1,200 meters long. So you would have to have some intermediate anchors and, actual end anchors of the slabs and intermediate pour strips in between to stress the slabs along the length. Because for something of that length, you would have to, construct it in sections anyways. You can't get that much concrete to do all of that in one pour, no matter what. So those would typically be with discontinuous portions of tendons. But again, our colleagues at CCL would be able to weigh in and provide the most optimized and practical approach to those types of projects.
Okay, and this is the final one that I see currently from John. What is the loading consideration at corners and free edges?
It is very good. No, I mean, I think that would be the same as what we do right now. So, currently with a Dramix approach, we look at the corner and free edge approach from a Dramix only condition, and I think we would do the same. So we would just evaluate all of the boundary conditions. If you do actually have, some kind of loading constraint that we would want to evaluate, then we would certainly be able to do that in much the same way that we do right now.
Great. I have asked the chat if there's any more questions. Looks like we have about 3.5 minutes. And here we go with Terry. Do you have literature available regarding sustainability to share with our clients?
Oh, definitely. So we have a number of different tools. We have the EPD that I mentioned that I can share with you. That's the Environmental Product Declaration. That's something that we can provide, as well as we've partnered with an online tool called One Click LCA. So the LCA stands for Life Cycle Carbon Assessment. It's failing me at the moment. I think that that's correct. So basically, we have an opportunity to actually calculate the actual GWP of using a Dramix SigmaSlab solution compared to a Dramix CombiSlab, or a fiber only compared to a conventional solution. There are tools in place that we can support you on doing that. So if you have a project that you'd like to evaluate this condition, just depending on where you are in the world, if it's me or your regional sales engineering team at Bekaert, just reach out to us and we can help you to provide whatever that data is to help promote the use of this solution with your ownership team.
Okay. David says, thank you, Claire, Nick, and Jan. Very interesting and informative. Thank you, David, for tuning in. We have 2 minutes. If anyone else has a question, I want to thank you guys again for joining, and hopefully you learned quite a lot. And if you have, if after you come up with questions, don't hesitate, just email myself or Claire, and we'll get back to you guys very, very quickly. Nothing yet, so might be our last one.
All right, well, if that's the end, then I guess we can go ahead and wrap here. Thank you all so much for joining today. We really appreciate you taking the time with us, and certainly look forward to talking about projects with you in the future. Please do reach out to me or Nick if we can support you on projects moving ahead. And have a great rest of your day.